Hello dear students, this is your engineering mathematics 3 lecture. Today's topic is inversion integral method. This is the method used to find the inverse Z transform. This is the second method. The first one, partial fraction method. In previous lecture already we have discussed partial fraction method. Now inversion integral method. This topic is from second unit. Now what is inversion integral method? Inversion integral for inverse of Z transform is given by the formula is the inverse Z transform is given by f of k is equal to summation residues of f of z into z raised to k minus 1 at the poles of f of z, where residue for r times repeated poles at z is equal to a is the formula to find the residue, calculate the residue is residue is equal to 1 upon r minus 1 bracket complete factorial into r minus 1 derivative with respect to z of the bracket term z minus a to the power r into z raised to k minus 1 into f of z bracket complete at z is equal to a. This is the formula to find the residue. And the inverse Z transform is nothing but addition of all the residues of f of z into z raised to k minus 1 at the poles of f of z. Now residues of, we calculate the residues of f of z into z raised to k minus 1 term. Already f of z term will be given in the example. You multiply that term by z raised to k minus 1 and then you find the residues of the term f of z into z raised to k minus 1 at the poles of f of z. You first find the poles of f of z. After finding the poles of f of z, you find the residues of f of z into z raised to k minus 1. After finding the residues, you just do the addition of all the residues. That is nothing but your sequence. Your required inverse Z transform. Sequence means inverse Z transform. And how to calculate the residue at the poles of f of z? This is the formula. If that residue is repeating r times, then r is for the repetition, r times repetition. So the formula is 1 upon r minus 1 factorial into r minus 1 the derivative with respect to z of z minus a raised to r into f of z into z raised to k minus 1 as z is equal to a. Now you see the example. Find inverse Z transform of 1 upon Z minus 2 into Z minus 3 by inversion integral method. For example, we're going to find the inverse Z transform. So here the bracket term is nothing but Z transform, and we use the notation for Z transform f of Z. So let f of Z is equal to 1 upon Z minus 2 into Z minus 3. Now you find the poles of this f of Z here. Now how to find the poles of f of Z? You just equate the denominator equal to 0. The denominator is z minus 2 into z minus 3. You equate it equal to 0. And if you equate it equal to 0, z is equal to 2 and z is equal to 3. These are the poles of f of z. Now z is equal to 2 and z is equal to 3. These are the simple poles because the degree of every factor is here 1. So these are the simple poles. Degree is 1 for every pole, then it is called a simple pole. So z is equal to 2 is a simple pole, z is equal to 3 is a simple pole here. Okay, now we find, see the formula, we find residue of f of z into z raised to k minus 1 at the poles of f of z. Now there are two poles, 2 and 3. We find the residue of f of z into z raised to k minus 1. So you find the term f of z into z raised to k minus 1. Now your f of z is 1 upon z minus 2 into z minus 3. You multiply it by z raised to k minus 1. So it is z raised to k minus 1 upon z minus 2 into z minus 3. Now the residue of z raised to k minus 1 into f of z at z is equal to 2. Now there are two poles, z is equal to 2 and z is equal to 3. So the residue of z raised to k minus 1 into f of z at z is equal to 2 is c. Here z is equal to 2 is a simple pole. So the value of r is 2. See. z minus 2 to the power 1, z minus 3 to the power 1, means the value of r is 1. So if r is equal to 1, then how to find the residue? R is 1 means 1 minus 1, 0. 0 factorial is 1. So this first term 1. Again, R is equal to 1. So 1 minus 1, 0. D raised to 0 means 1. So this term is also 1. In bracket, Z minus A. A is the pole. Now here, the pole is 2. So Z minus 2 to the power 1, because R is 1. Z minus 2 into f of Z into Z raised to K minus 1 time. So here, the residue of f of Z into Z raised to K minus 1 at Z is equal to 2 is 3. In bracket, Z minus 2 into f of Z into Z raised to K minus 1. Now f of Z into Z raised to K minus 1 is this term, Z raised to K minus 1 upon Z minus 2 into Z minus 3 at Z is equal to 2. Now put Z is equal to 2 here in place of Z. When Z is equal to 2, it is 2 raised to K minus 1 up, and this Z minus 2, Z minus 2 get cancelled. 2 raised to K minus 1 upon Z minus 3, Z is 2. So 2 minus 3 is minus 1. So it is minus of 2 raised to K minus 4. This is the residue of Z raised to K minus 1 into f of Z at Z is equal to 2. Now residue of Z raised to K minus 1 into f of Z at Z is equal to 3. At Z is equal to 3, you find the residue. Similarly, here R is equal to 1 for Z is equal to 3, because 3 in the denominator, the term is Z minus 3 to the power 1, means R is equal to 1. So Z is equal to 3. Here is a simple pole, so R is equal to 1. So similarly, the residue of at Z is equal to 2. We can find the residue at Z is equal to 3. It is equal to Z raised to K minus 1 into f of Z into Z minus 3 at Z is equal to 3. Now you know the term Z raised to K minus 1 into f of Z. It is here Z raised to K minus 1 upon Z minus 2, Z minus 3. So the Z minus 3 get cancelled, and the term is here Z raised to K minus 1 upon Z minus 3. So put Z is equal to 3. If you put Z is equal to 3, it is 3 raised to K minus 1. And this Z minus 3 get cancelled. 3 minus 2 is 1. So the after simplification, the term is 3 raised to K minus 1. And so the sequence is f of K is equal to sum of all the residues of f of Z into Z raised to K minus 1. And sum of algebraic sum of all the residues of Z raised to K minus 1 into f of Z is minus 2 raised to K minus 1 into 3 raised to K minus 1. Where K is greater than or equal to 1, mod Z is greater than 3. Condition. We need to write the condition, because the condition of Z is not given, so no need to write, because in partial fraction we write the conditions of Z as well as the conditions of K. Similarly, we can find or obtain the sequence f of K by use of inversion integral method, when f of Z is given by f of Z is equal to 10Z upon Z minus 1, Z minus 2. Okay. We can solve this example like the previous one. We get the answer here. Now next topic in this unit is solution of difference equations with constant coefficients using Z transform. Now solution of differential equations with constant coefficients using Z transform. The results are here, some results. Z transform of f of K is equal to f of Z. Z transform of f of K plus 1 is equal to Z into f of Z minus Z into f of 0. Z transform of f of K plus 2 is equal to Z square into f of Z minus Z square into f of 0 minus Z into f of 1. Z transform of f of K minus 1 is equal to Z raised to minus 1 into f of Z. Z transform of f of K minus 2 is equal to Z raised to minus 2 into f of Z. Note here, f of K is considered as a casual sequence. Okay. Obtain f of K. Example, obtain f of K given that f of K plus 1 plus 1 by 2 f of K is equal to 1 by 2 raised to K greater than or equal to 0, f of 0 is equal to 0. Now, this is a difference equation. We are going to solve this difference equation using Z transform. Now, taking Z transform on both sides, we get Z transform of f of k plus 1 plus 1 by 2 into Z transform of f of k is equal to Z transform of 1 by 2 raised to k. Now Z transform of f of k plus 1 is Z into f of Z minus Z into f of 0 plus 1 by 2 as it is Z transform of f of k is f of Z is equal to Z transform of 1 by 2 raised to k. 1 by 2 raised to k when k is greater than or equal to 0. It is Z upon Z minus half. Mod Z is greater than half here. So here the value of f of 0 is 0. So put f of 0 is equal to 0. So Z into f of Z plus 1 by 2 into f of Z is equal to Z upon Z minus half mod Z greater than 1 by 2. When k is greater than or equal to 0, the condition for Z is mod Z is greater than mod A. The value of A is here 1 by 2. Okay. So it is the f of Z is common in LHS side. So you take it common. So remaining term is Z plus 1 by 2 into f of Z is equal to RHS term Z upon Z minus half. Okay. Now you transfer this term Z plus 1 by 2 in RHS, so that you will get the value of f of Z. It is equal to Z upon Z minus half into Z plus half. Now we are going to perform here the partial fraction method to find the inverse Z transform, because we are going to find the sequence. Now to find the sequence, we have to find out the inverse Z transform. And to find the inverse Z transform, there are two methods: partial fraction and inverse Z integral. Where condition of Z is given, condition of K is given. So we are going to use the partial fraction method here. Now we do the partial fraction of f of Z upon Z. So we transfer the Z in LHS, in denominator of LHS. So the term is f of Z upon Z is equal to 1 upon Z minus half into Z plus half. Now you separate these two terms in RHS, denominator of RHS, by using partial fraction method. To separate the terms are 1 upon Z minus half minus 1 upon Z plus half. Okay. After doing the partial fraction, you again shift the Z in RHS, so that the term is f of Z is equal to Z upon Z minus half minus Z upon Z plus half. Okay. Now the inverse Z transform for this sequence is here. One correction is there. Right here. Inverse Z transform of f of Z. Inverse Z transform of f of Z means apply here inverse Z transform on both sides. So inverse Z transform of f of Z is equal to, now inverse Z transform of Z upon Z minus half is 1 by 2 raised to k. Using the Z transform of standard sequences results, you can easily write here that Z transform of Z upon Z minus half, it is 1 by 2 raised to k minus inverse Z transform of Z upon Z plus half. Z plus half means we can write this Z plus half as Z minus of 1 by 2. So it is minus bracket minus half raised to k, where k is greater than or equal to 0. We are using for these two terms Fourier transform results, Fourier transform of some standard sequences results here, and we have the answer 1 by 2 raised to k minus 1 by 2 raised to k when k greater than or equal to 0. This is the inverse Z transform of f of Z. Okay. These are the sequence. There are two times sequence. So here difference equation topic is also covered. We want to solve one more example of difference equation. So here try to solve. Obtain f of k given that 12 f of k plus 2 minus 7 f of k plus 1 plus f of k is equal to 0. k greater than or equal to 0, f of 0 is equal to 0. You take it as a homework. You try to solve. First, you taking the transform on both sides, and then after finding f of z, you again apply inverse the transform on both sides, and then you will get the sequence. So in difference equation, we use both the transform. First Fourier transform and then inverse Fourier inverse Fourier sorry. First we use the transform and then inverse the transform, both the transform to find the sequence. So all the topics of the transform are over here, and the second unit is also over here. Thank you.